Hi, and welcome to the domain-specific hardware section. In this video, we will talk about the role of hardware, evolution of computer architectures, and our section content. Here we go. There are three rocket stages that launch deep learning revolution: algorithm, data, and hardware. All three stages are essential. The absence of one of them would have made this revolution completely impossible. Algorithm stage is about how to develop efficient deep neural network architectures and how to solve miracle problems of its training. World-known pioneers of deep learning, Jan LeCun, Yosha Bengio, and Geoffrey Hinton, and their research in convolutional deep neural network and error backpropagation training. Algorithms are probably the most important part, but still, it's just the first stage. The second stage is data. To train complex models with millions of parameters, you need gigabytes of labeled data. If your dataset is not big enough, the model will just remember it without any learning process or generalization. To produce and label big dataset, you need huge amount of combined human resources. And these resources were simply not available 20 years ago. Compare, the MNIST handwritten digit database appeared 20 years ago and had 70k images in 10 categories. Today, ImageNet database holds 14 million images in 20k categories. Commercial giants like Google maintain even bigger private datasets. And the last, but not the least stage, the relevant hardware. Andrew Ng was the first who offered large scale of GPU to accelerate deep neural network training. You can't imagine any DNN research, Kaggle competition, or machine learning company that doesn't use GPUs. Like many other ideas, deep learning had been waiting for decades before suitable hardware became massively available, both for academia and commercial usage. Today, CPU and GPU-based computers are default option for the majority of developers, starting from student enthusiast up to commercial giant. But CPU and GPUs are still very general. GPUs can be used not only for DNNs, but also for gaming, cryptocurrency mining, movie rendering, or even computational fluid dynamics. Can we develop hardware not for the general purpose, but solving some particular group of problem, or some domain task? Yes, we can design custom hardware for machine learning application. And that's the topic of this section. Today, the domain-specific hardware is a crucially important point. It's where DNN revolution meets computer architecture challenges. Let's have a brief overview of computer architecture eras. One of the first Intel CPU was released in 1975 and had frequency of 1 MHz. Thanks to Moore's law and linear scaling, CPU performance has been growing exponentially for 30 years. Pentium 4, released in 2005, had 4 times higher frequency, 4 GHz. This was the first single-core megahertz era. For sure, Pentium 4 is not just a faster version of 286 processor. There were many conceptual features implemented: superscalar capabilities, vector instructions, auto-further executions, multi-threadings, and so on. But the key driver was still megahertz growing. The last decade we've been living and live today in the multi-core era of parallel computations. Both CPU and GPUs demonstrated performance growth with more and more complex multi-core design technique. And it looks like the era is also close to its end. The industry needs something else, new architectures, not a linear increase of the amount of cores or hertz. As Dave Patterson, the world's most famous computer architecture specialist, said last year, we see today a Cambrian explosion of novel computer architectures. The Cambrian explosion refers to the sudden appearance in the fossil record of complex animals 500 million years ago. All major animal body plans we see today appeared during this time, changing the biosphere forever. Cambrian explosion formulated the body structure of a starfish, octopus, and us, the hardware developers. In computer architecture, it means the beginning of completely new architecture structures. That's where we are today. Machine learning challenges and novel computer architectures meet together. As you know, there are two stages in the machine learning development: the training stage, when you teach your model on the labeled data, and inference or prediction stage, where you apply your model to some new data. And also two places where you can do it: on the edge and in the cloud. Cloud means some remote server facilities, and edge is something very close to your data source: computer vision camera, smartphone, fitness tracker, autonomous car, or your quadcopter. Cloud solutions for machine learning hardware require big and powerful computational chips and interconnect facilities, combined into the giant supercomputers specifically for very fast DNN training and massive inference application. Edge solutions are in the most cases used only for inference, and more focused on the lowering of power consumption, chip space usage, and latency of single prediction. To build application-specific hardware, instead of general CPU and GPU usage, you may achieve higher total performance or higher performance per watt, decrease prediction latency, and achieve higher throughput. It lets us training model faster and makes predictions quicker. In order to achieve it, we must escape from CPU and GPU architectures and build something really new, and solve a lot of conceptual challenges. And it's not only theoretical studies. Google has already developed 4 generations of their custom chip, Tensor Processing Unit or TPU supercomputer. Google actively uses it in production and theoretical research. BERT, the natural language processing model, was trained on the TPUs, not GPUs. Microsoft heavily invested into cloud solution based on FPGA chip cards and combined them into supercomputers to achieve very low inference on a single prediction. Moreover, Microsoft develops hardware description language specifically for AI computers development. Facebook started development of its own AI chip a couple of years ago. Apple and Huawei insert coprocessors into their smartphones and smartwatches chipsets. And this area is not only for the big companies. There are dozens and dozens of the successful startups across the world in this area. GraphCore in the UK, Grok in the US, Habana Labs from Israel. The last one, it was only a 3-year-old startup. It was acquired by Intel for $3 billion. In this section, we will tell you who are the main players on this market, both young and young companies, how to develop own tensor processing unit chip, what sort of challenges and bottlenecks exist on this track to more efficient architectures, how to evaluate your machine learning hardware performance, how to compress your model to fit it a specific hardware, and more extra materials. Welcome and hope you like it!